Hi guys, in this video we are going to learn about DC load line as well as the voltage versus current characteristic of a diode. In the previous video we have learned the basic introduction of diode. If you haven't watched those videos, I have given the link in the description so you can always watch that. And also another kind request, if you are new to this channel, please don't forget to subscribe Expert Tutor. So without wasting our time, let's move into this session. So first of all, we have already discussed when there is a diode to make that diode work, we need to give a forward biased voltage. So if we are providing a forward biased voltage, we should give at least 0.7 voltage for silicon, otherwise it won't work. So if you are providing more than 0.7 voltage, what will happen to diode? So first of all, we need to know what's going to happen. Let's say you are going to provide 0.7 voltages so that the depletion range of that diode will be cancelled out, which means in the beginning there will be a depletion region which we have already studied. So I'm not going to go very slow. So it's going to be like this. So there is a minus and there is going to be a positive charge, and there will be the minus n-type semiconductor, but always remember there is going to be germanium or any atoms which is having 5 electrons, 5 valence electron. So what we have done is we have connected to the forward bias, which means we are going to give the positive voltage to the positive side of the diode as well as negative voltage to the negative side of the diode. So once you are connected with that, we are going to provide some voltages so that this depletion region will be cancelled out if you are giving a 0.7 voltage if it's made by silicon. If that's germanium, the depletion region voltage would be 0.3 voltage, so that if you are providing 0.3 voltage across this diode, this depletion region will be cancelled out. So let's say you are providing 0.7 voltage because this is a silicon, and what's going to happen is the depletion region is no more there. So there's going to be positive. Always remember which mean by this P, and this is going to be, we are marking like this negative, which means there is going to be n-type, which means there is germanium, as well as in this position there is boron, but that's not positively or negatively charged in this NOP type conductor. So when there is an electron over here, we are providing 0.7 voltage across this, so it's going to be 0.7 voltage. If you are providing a 0.7 voltage, the depletion region would be automatically cancelled. And another important thing is, if you are providing 0.8 voltages, there are no resistance, so that there won't be 0.1 voltage. It cannot handle that 0.1 voltage. Let's say you are providing a 10 voltages. So what's going to happen to this diode? Actually, it can't handle this 10 voltage because there are no resistance. So in a short, let's say there's a short wire and you are providing 10 voltages to this short wire, what's going to happen? It can't handle, so that battery will directly lose the power. Likewise, if you are giving a high voltage to this semiconductor or a diode, what's going to happen is it's going to burn out. So for even though you are providing in a forward bias, what you should do is you need to maintain the voltage little bit approximately similar to this 0.7 voltage. It might be little bit higher or little bit lesser. But if you are providing a higher voltage than this forward bias voltage, let's say you are providing 10 voltage as a forward bias voltage, the diode is not going to work anymore. It's going to be burned out. So what we are going to do is we are going to see what voltage the diode can handle and how it's going to work. So if there is a diode, you can directly tell there is going to be some characteristic for that diode, how it's going to work with the voltage and how the current will vary with the voltage. So that's known as voltage versus current characteristic graph. So we are going to learn about two graphs. So you need to remember what's the difference between these two graphs. So first one is characteristic graph, which means if there is a diode, for any diodes, it's going to work in a particular manner. If there is a silicon, you need to give 0.7 voltage, and also it will be notified by the manufacturer of that diode. So here I have got one characteristic graph. As you can see over here, It's starting from this is known as the voltage of the diode, the forward bias voltage you are providing. And if you are providing in this side, you are going to tell reverse bias voltage, and this is going to be the forward bias voltage current. So you are providing like this. So let's say you are going to provide a 0.5 voltage nearly here. In this point, you can actually see there are no such current. It's very few. If you are providing 0.7 voltage, the current is higher. And also, if we are a little bit higher than the 0.7 voltage, the I is going to go at a very peak range. But if you provide 1 voltage, there are no graph, which means it can't work. It will already burnt out. So you need to make sure that this diode is going to have only the voltage between a certain level, let's say until 0.75 or 0.8 voltages, because it can't handle. If you provide more, it's definitely going to burn out. In the next side, if you are providing a reverse bias, it can handle up to a higher voltage than this forward bias voltage. Let's say it's nearly 2 voltage for silicon. But anyhow, if you are providing reverse bias voltage, which is more than that voltage, which is normally known as knee voltage. So if you are providing the reverse bias voltage, which is more than knee voltage, it's going to definitely break down so that the current can flow. So it's like a short circuit. If it's breaking down, it's going to allow all the current throughout this diode. So it's going to be like this. So that's the basic concept. So you need to remember, this is a very simple graph. If you are providing forward bias, you need to have at least 0.7 voltage to get a current, and you need to change. You can vary for a certain limit. If you are providing much, it's definitely going to burn out. In the reverse bias, there is a voltage that's known as knee voltage. If you are providing higher than that voltage, it's definitely going to burn out, and it's going to provide the current through that diode further. So that's the main thing you need to understand about the voltage versus current characteristics. So let's move on to this one. So now we have learned about voltage versus current. So I hope you have understood this one. So now let's check up with the DC load line of the diode. So in the first explanation, I have already mentioned, when you are using the diode, you need to make sure that the diode is going to have or will have only 0.7 voltage or little bit near to that. So let's say you are providing the voltage source over here, and there is a diode. So actually we knew that this is going to be the plus side of this battery, and this is going to be the negative side. So that I have already told this is going to be the positive terminal, and this is going to be minus terminal. So please pause the video and try to guess, is this a forward biased or reverse biased? I hope you have got the answer. It's definitely positive. It has been connected to the positive terminal of the voltage as well, so that it's going to be forward biased. So if this is forward biased, we actually knew that it can only handle up to 0.7 voltages. So let's say you are providing 2 voltages, definitely this diode is going to burn out because it can't handle these 2 voltages. So how to make this circuit a little bit better to handle a voltage, a higher voltage limit? Let's say if you are providing 2 voltage, it's not much higher than the 0.7 voltage, but diode can't handle that. So what you can do for maintaining this voltage? So that's why what we are going to do is we are going to connect a resistor with that. So let's say if you are connecting a resistor with R, and there is a voltage across this diode, so let's make that silicon, and this is 2 voltages. If you are providing the 2 voltages source, what's going to happen is across this silicon it can only use this 0.7 voltage. So for the 1.3 voltages, what's going to happen for the 1.3 voltage? Again, please pause the video and try to figure it out what happened for 1.3 voltage. So in this case, the 1.3 voltage can be lies between this R. So this is going to be happen. So if you are neglecting this resistor, if you are not putting this resistor in this circuit, definitely the diode can survive. So that's the main thing. That's why we are going to add a resistor in series of diode. So there might be some questions. you are telling these things about diode. There are so many characteristics. So why we need to learn about that, and what's the use of this diode? Diode are the basic thing, and this is used to build transistor. In the next sessions we will be learning transistor. That is the very basic thing, and we are going to build the transistor using the techniques which we have learned from this diode. And another important thing, with this diode we can make AC voltage into DC voltage. And another important thing is, we have already learned that the diode is going to provide the current in only one direction, so that it's very simple and it will keep the circuit very secure. So let's say you are having some instruments, and that instrument is going to provide the power. And another important thing for that instrument is, if you provide the current into that instrument is going to burn out. So in that circumstance, what you can do is, you can put a diode forward bias with that instrument, so that it will make sure, the diode will make sure there won't be any current is going through this diode or to that voltage or the instrument. So here I have marked all the things. So let's mark it like this. This is going to be E, and this is going to be the diode voltage. Normally it's going to be 0.7 voltage, and this is R. And let's mark the current as I. So I'll tell you why I'm marking these things. So for what's meant by the DC load line is, actually we are going to mark the voltages, and we are going to equate the voltages across these thing, across these circuits. So if you mark that, it's going to be E would be equals to, which means these two voltages would be equal to, in this side we can move, here it's going to be I into R plus, this is in this direction, plus VD. You might be wondered why I have marked in this in this side 0.7 voltage as, and in this side 1.3, but here I have marked like this. That's very simple. But never, let's say this current is moving towards this side. So in which side the voltage is going to increase? So in that direction we will normally mark the voltage side. So here across this diode, the voltage is going to increase in this direction. Likewise, if you are considering from these 2 points, the current is moving from this path to here. The current normally move from the higher voltage to less voltage. So how we can mark the voltage line is, it's going to move from here, from the low to high. We need to mark it from the lower part to higher part. Likewise here, we knew that it's going to be minus and it's going to be plus, so we can directly mark this is going to be minus to plus. So you can see that this 2 voltage is going to be equals to this voltage plus this voltage. That's why we can put IR is equals to IR plus VT. So that's the important thing you need to notice. I hope now you have got a little bit idea about these things. And here that E is going to be constant if you are providing a constant voltage, which is a DC voltage or constant voltage especially. And the V diode, to if the circuit is working, the V diode, the diode voltage, the voltage across the diode is going to be a constant. It's going to be 0.7 voltage, and it might vary a little bit. So we are going to check how can it change. So that's the main thing. And another thing, the R is going to be constant over here, and I will vary a little bit, can vary a little bit if the voltage across the diode is varying a little bit. So what we are going to do is, we are going to check the graph for BD, and we can mark this I as ID. The reason is, this current, the current through this resistor is going to come through this diode, so that we can directly tell the current would be equals to the current goes through the diode. So we can mark it like ID. So if you change this equation, if you subject ID, you are going to get an equation like this. ID is equals to E minus BD, and if you divide it by R, you are going to get like this. So I'll mark it over here. ID E over R minus BD over R. Now we are going to plot a graph for VD versus ID. So this is going to be R into VD, and there's a minus sign, plus E over R. So can you guess what's going to be this graph? So these are constants, and I need to know how the current is going to change with the voltage across the diode. So please pause the video and try to mark it. I hope you have clearly understood that this is going to be a straight line graph, because this is going to be y and this is going to be a constant m, and this is going to be x plus c. But always remember, the m is in the negative, m is having, the gradient is having a negative inside that, so that the graph is going to be like this, in this direction. This is going to be id and vd. So according to that circuit, you can assume if the voltage is here, the current should be in this point. If the voltage is over here, the voltage between the diode is over here, the current is going to be this side. But another important thing is, what's this? We have already learned a graph, and now we are going to learn another graph. We have learned another graph for ID and BD. So what's the truth one? So whether this is the truth one or that one is the truth one. So the important thing is these two are truth, which means the diode can only work with these things, because this is the graph provided by manufacturer, and according to this only the diode can work. But in that case, what we have taken is, in that circuit, in that particular circuit, how it's going to work. If you are providing another circuit, definitely this graph is going to be changing a little bit, because if you are providing, let's say you are increasing the voltage to E by another 5 voltage, the interception E by R is going to increase, so that this time this might be coming in another direction. So always remember that. So this graph will change according to that circuit. In that circuit, if you are providing the diode voltage like this, voltage across the diode like this, you are going to get over this point. So it might vary within your circuits you are taking, and this is the graph which is given by the manufacturer of the diode, and the diode will function according to this graph. So how to find in what point the diode is going to work? So what you can do is, you need to plot the same graph, that graph we have taken from that circuit, in the same graph, so that you can notice there will be a point that these two graphs will intersect. So that point is known as the Q point, intersection point, which means if you are providing a diode in that circuit, in a particular circuit, it's going to work, the diode voltage would be nearly in this point, and the current through that ID would be here. So that's how we will find the current which is going through this diode in a particular circuit. So that line is known as DC load line. So you need to remember the names. The first one is, it's going to be different DC. This is going to be DC load line. And the first one is characteristic graph, which means the diode can only work with that character. You can't provide, like here they have mentioned, you can provide this voltage. If you provide this voltage, you are going to get this. But it's not going to happen actually. In that circuit, it can survive if there is it's like a resistor. It's considering as a resistor. We are considering as a resistor in that DC load line curve. If there is 1.3 voltage over here, that resistor, the diode is going to have 0.7. If that another resistor is going to have 1.2 voltages, that resistor will have, let's say, 0.8 voltages. So it will only check, it will consider that diode as kind of a resistor and give a DC load line. But always remember, it can't work. The diode can actually work in that voltages, because we already knew it can't go either rather higher than this. So that we will plot these two graphs in one graph, and we can figure it out at the point, intersection point of these two graphs. We are going to tell this is going to be voltage of that diode which is working. Let's say when it's working, you are going to change the voltage across the power supply voltage little bit. So if you reduce the voltage, what's going to happen is, we actually knew that the E over R is the interception, so E over R will be reduced, so that it's going to be like this. So in this case, in the previous one, let's say it's going to be like this. So you can directly see that here what was happening is, in the initial position, it's working, the diode is working on this position, and after that, in that circuit, when we are increasing the power supply voltage, the voltage across the diode has been increased little bit. So that's the thing, the characteristic graph won't change with the circuit. It's a fixed one. The diode can only work in that region, but the characteristic can graph, sorry, the DC load line graph can change, but always remember, it doesn't mean it's going to work through all the line. It can't work. We will see the intersection of these two graphs and figure it out what's the point. And another important thing, that point is known as Q point, quiescent point, the active point of that diode, which means in which point the diode is working, in which voltage and in which current is going through the diode. So that's known as quiescent point. So we simply call as Q point of that diode. I hope you have learned something new through this video. If you have any doubts, please comment it below, and I'll see you in the next video, and don't forget to subscribe it. Thank you for watching.